The conversation with Professor Valentin Troll. We are very lucky to have him on board. Please give him a warm welcome to the stage for his conversation, the youngest ocean on the planet and making the Atlantic.
Thank you so much. Thank you for the introduction. Thank you for joining me this afternoon. If I had my free choice, I would probably curl up in my bed right now with that swell. But no, my daughters gave me these sea bands, and they do miracles. So I feel quite up for the challenge now. And I'd like to talk about the youngest ocean on the planet, which, of course, is the Atlantic Ocean. And it's, of course, a major ocean. It's a big ocean, but it's nevertheless a youngster when it comes to the oceans of the world. Well, it's the second largest ocean, despite being the youngest, and it covers about 20% of the Earth's surface. And it hosts about 29% of the Earth's water. And, well, it stretches from, let's see, does this work? Can't see a pointer, but we'll make do without. It stretches from the southern tip of South America all the way up to Iceland and Greenland and even further north. And it's, of course, separating North America from Europe and Africa from South America. And it's the youngest of the 5 main oceans, and it started to form in the Jurassic period. This is back when the dinosaurs roamed the Earth some 150, 160 million years ago, and it followed from the breakup of Pangea, the entire Earth, and there was a supercontinent back then. I should point out that the Earth evolves in supercontinent cycles. Before Pangea, there was a different supercontinent called Rodinia, but let's not go too far right now. And there was a time back prior to the Jurassic where all the continental landmasses were united. And this was Pangea. Well, just to give you a flavor, the United States is less than 1/6 of the size of the Atlantic Ocean, and the Atlantic Ocean is generally agreed upon to be the first major ocean that was crossed by plane and by ship. And we'll talk a little bit about that later on as well. So here's the Atlantic Ocean, and the pointer, I think here on the black we'll see it, but not elsewhere. So it's marked by this spine, this geological spine, the mid-Atlantic ridge. And this is where the Atlantic spreads, and it spreads very gently with about 2 centimeters a year. The Pacific being a much older ocean, and the Pacific being a really mature ocean, it spreads at about 7 centimeters a year, so the Atlantic hasn't actually geared up to full speed yet. So this Pangea idea of the supercontinent Pangea goes back to this gentleman here, Alfred Wegener, and he was heavily criticized for this back in the days. He postulated this 1915, 1910, round about that turn, so well over 100 years ago, and he argued that the continents can be moved together. They fit like a jigsaw puzzle, and they drifted apart, and he called it continental drift. The major criticism he received was for a lack of a mechanism. People said, how would that work? Back then, there was no understanding of continents moving laterally. And he pointed out that there was fossil evidence. There's fossil species that continue over South American borders into Africa. And he argued these must have been provinces that were together. And he made similar observations with fossils from South America, Africa, Antarctica, and into Australia. And this was one of his main line of evidences where he said, look, these things were joined in some giant landmass. And only in the 1960s, 1970s did his ideas get fully accepted. And it started off some 100 million years ago. There's a little reconstruction starting there with 80 million years ago. Once the Atlantic started to form, it drifted these continents apart, and eventually a proper ocean formed. So here we see Pangea in the top left as a unified landmass, and then it's split up into major continental blocks. Laurussia is nowadays North America and part of Asia, and Gondwana being South America, Africa, and Australia. And eventually these continents are drifting apart to form what we see at the present day. If this theory is correct, then some point in the geological future, all these continental landmasses will come together again, and they will make another supercontinent before it splits up again. So, but this is very far in the future, and here we can look at the age of the lithosphere, the age of the rocks underneath, and you see Greenland and Scandinavia here in the top left of the grey and black panel, and there the red is young material forming, and their spreading started some 100 million years ago, and it's still going strong, and Iceland sits right there in the middle, and you see in panel F, Iceland is actually at the youngest part of this spreading center in the North Atlantic. So how does this spreading go about? Well, there is these spreading centers, and they span through all the major oceans. It's a ridge system that's about 60,000 kilometers long, and it hosts some 85% of all the Earth's volcanism. So the volcanism we see on the continents is only about 14, 15, 16% of all the volcanic activity on the planet. And here in the Atlantic, we see the spine going down all the way. It wobbles a little. It's not a straight line. It's marked by many little faults. We call them transform faults that shift the ridge laterally a little bit. But it goes through the entire Atlantic. And at these spreading centers, the hot mantle is welling up, and it pushes the plates towards the left and the right, and this is where magmatism then takes place. So we know about this spreading because when rocks form, igneous rocks, magmatic rocks, they contain tiny little minerals of iron oxide. And the iron oxide will actually orient itself according to the magnetic field. And the magnetic field is changing throughout Earth history. And depending on when the rock solidifies, we have positive or negative polarity in the rocks. And if you do a magnetic map of the oceans, you actually find it's stripy because the rocks have formed at slightly different times. And this is the stripy pattern here in the center image, where the fresh rocks would have a certain polarity, and somewhat older rocks that have already been pushed away have a slightly different polarity, and yet older rocks that are yet further away have yet again other polarity. So these mid-ocean ridges forming 60,000 kilometers of ocean ridges, and as I said, they host some 85% of all volcanism on Earth, and there is an eruption almost any given point somewhere along this system. So initially, these things start up as little continental rift zones, as continental breakage zones, and eventually they widen, and then finally they make oceans. And we, in geology, we work with analogs, and one good analog for a continental rift is the East African rift, as you see in the top right here. That's where we are breaking a continent apart. Another one of those is actually the Rhine and Rhone Graben in Europe, where Europe is breaking apart. But it's very, very slow, and the European one, well, there's good chance it might get arrested. It might actually never become a real ocean. But the East African one, it starts to make an ocean because we have the Afar Triangle, and the Red Sea is actually where water has already crept in. This is where the spreading has continued to a point that an ocean is in the making. And eventually, once the spreading has continued for many millions of years, there is a real ocean like the Atlantic. And we talked about Iceland being a very special case, being a plume that pushes up a ridge, and therefore we can see it. And in Iceland, we see this ridge system on land. So here, the lower two images showing the breakage zone, the fracture zone that is exposed on Iceland, and it's a large regional feature, very impressive. And on the western side of Iceland, you're of course on the North American plate, and on the eastern side of Iceland, you're on the Eurasian plate. So, why in Iceland? Well, I mentioned it, it's because Iceland is a bit special. It's not just the ridge, it's also this anomaly, this heat anomaly coming from deep inside the earth and pushing up. We call it a mantle plume. Some people like to call it a hotspot. Some researchers even think there's a difference between a mantle plume and a hotspot, but that's a bit of semantics if you ask me. And the Iceland plume is going strong for quite some time, at least 70 million years. And there's some reconstruction here. Initially, the Iceland plume may have had two arms. We talked about it very briefly. But nowadays, it's got one major stem, and that sits under Iceland. And it produced a lot of rocks that are now exposed in the ocean. It makes the Iceland Faroe Ridge on the one side and the Iceland Greenland Ridge on the other side. And the gray areas here in that map, they are the submerged volcanics from the Iceland hotspot. They are now underwater, but they are elevated banks of materials that are of magmatic rock, and they go back to previous activity of the Iceland plume. So, but the beauty about Iceland is you can walk inside this mid-Atlantic ridge, which otherwise is always underwater. And if you follow towards the coast of Iceland, you'll actually see how the water creeps in. And you can actually go even further. And if you are bold, you can even dive in there. You can dive in the mid-Atlantic ridge. And if you're super bold, you can go very deep there. I've never done this. But here we have divers exploring the fracture zone of the mid-Atlantic ridge of Iceland. And you can go quite deep if you want, I'm told. And eventually, if you were to follow this all the way down to the ocean floor of Iceland, you would come to the main ridge system at the ocean floor in the center of the Atlantic. And the Atlantic is about, on average, 3,300 meters deep. And the deepest point is actually off Puerto Rico with 8,600 meters. Most of the mid-Atlantic ridge is actually at about 3 kilometers depth. So this is like a mountain zone underwater in the Atlantic. It's not very deep, it's actually elevated. And here in the lower left, you see that there's this elevated ridge system that sits in the middle of the Atlantic Ocean, and this is where most of the spreading happens, and this is also where most of the volcanism happens. So, now, this is of course something we're researching for many years, and just this morning I went into my little picture library. So I've sailed on several research ships, like here the Poseidon and the Meteor, and I remember that we had some rough days there as well. So I put these top right-hand pictures in there for you to show you it's not quite so bad today. I've seen worse. So, and I didn't have any sea bands back then, I tell you. So, but here we can drill down into the ocean floor. We also have submersibles these days that take us down there. They can withstand the pressure, and they can actually take photographs, and they can take water samples, and they even can take rock samples from down there. So, and this gives us a good idea of how the mid-Atlantic ridge looks like. And in the lower right hand, there's an image of this little fracture system on top of this ridge. And there we have magmatism. We really have little submarine volcanoes there and little lava flows. And there is a little magma reservoir sitting underneath. And it produces little fissure eruptions and also, as I said, little volcanoes. And let me stress, we know from Iceland that a lot of volcanism on Iceland happens along fractures, and this is exactly what we need to expect from the mid-Atlantic ridge as well. On the left, I'm showing an image from the 2022 eruption on the Reykjanes Peninsula, and you can see that the lava comes up along a fissure, along a fracture. And then here's an image from the ocean ridge at 3,000 meters depth, and here's one of those fractures, and we see lava rock on either side of it. And every now and then, submersibles are happy enough, and they catch a little eruption. And of course, much to the excitement of the crew on the ship, then of course one has to be very careful to bring the submersible not too close but not too far away either. But here in the top right hand, you see the arm of the submersible, and you see a little bit of lava pouring out, a little pillow lava arm that comes out. And of course, it quenches immediately on the outside, making a dark crust. But when the crust is ripped apart, you can see the glowing material inside. So here are a few images of what it looks like under the ocean. And here is again one of those fracture systems and magmatic rock on either side. And this is in the crest of the ridge, of the mid-Atlantic ridge. And I showed one of those before. Here is a tongue of lava that is erupting. And we also have these smokers, as people call them. There is no smoke, of course, you're underwater. But this is hydrothermal fluids that are emitting. And we're distinguishing between white smokers and black smokers. I'll talk a little bit later about this in more detail. The white smokers have often tiny crystallites of calcite and silica, and the black smokers have tiny crystallites of metal deposits. So, and this is actually very important for potentially resolving some of our resource issues in the future. So here are a few shots from deep under the ocean. There's often pillow lavas because they look like, well, pillows, but this is quenched lava because when water gets in contact with the hot lava, then the lava freezes up and it flows in little tubes, making these pillows. And here in the lower part, we have a bit of a pohoi texture, a ropey lava, and the one in the top right, we have a more flat-lying surface of lava. And here we have pillow lavas, and of course they get fractures. And if you crack these pillows open, you see they have radial cracks, radial joints. Many of you have probably heard about the Giant's Causeway. This is a basalt lava with columnar jointing. This comes from cooling. Then the lava shrinks a little by 10%, and that means it cracks. And the cracks and the columnar joints are usually perpendicular to the cooling surface. And here, the pillows cool all around, so that means the cracks are actually perpendicular to the outer surface where the cooling happens. The picture in the lower right is very nice because there we have a pillow that then solidified and then eventually cracked open, and another arm or tongue of lava came out, and you can see that there. So this is how these lavas progress. They freeze over, and then they break out again, and freeze over and break out again. So, and here we have a few more images, and this is the arm of one of our little submersibles that takes samples, and this is usually done remotely. There is some where people sit in there, but for the really deep work, we usually don't have manned submersibles. We usually have automated, remotely controlled submersibles. And here's more pillow lavas. Let me stress there is a lot of submarine life in those areas as well, and these rocks are very quickly colonized, believe it or not. And here's a few more images. This is a very intriguing feature. This is actually lava crusts, and there must have been gas involved underneath. So this is lava crusts that have been inflating because of gas pushing this material up. And there's pillars of material in between the former giant gas bubbles. And if you take a sample from there, like in the bottom right, you see that the lava was still liquid and was pushed apart into these tiny little needles before eventually many of these needles would break and only some of the stronger pillars remain. This was a big mystery when the first submersibles brought footage from down there. And of course, initially people said, oh, Atlantis, a sunken city, but this is actually a very natural phenomenon. So I talked a little bit about this, black smokers. This is hot vents because when water creeps into these fractures and gets close to the magma source, the water will heat up and it will leach elements out of the surrounding rock, and the hot water then rises up, and when the hot water gets in contact with a cold seawater, you have a chemical reaction. A lot of the minerals that are dissolved in the hot water will start to precipitate. And it looks like smoke, but it's actually zillions of tiny little crystallites that form because of the temperature and pH contrast between the hydrothermal fluids and the ocean water. Here's a white smoker, and depending on what minerals are forming, the smokers have different colors, but as I said, there is no smoke involved. It's actually a chemical reaction involving mineral precipitation. Then I'm not a biologist, so I don't want to go into a lot of detail here, but some of the ocean floor communities are quite astounding. And this is also where scientists have discovered archaeobacteria. Now it turns out they're not bacteria at all. They are part of the group Archaea, and these are single cell organisms that live there, and they love the heat of the volcanic activity. And they digest energy from these systems, and it's believed that they could have been some of the very earliest life forms of our planet. And here's some images, and they are very happy at 190 degrees Fahrenheit and down to 0.9 pH. Very acidic conditions, very hot conditions, almost boiling point of water, and these little chaps, they're very, very happy there. So, having a look at the center of the ocean, we just looked at this red spine of the Atlantic. I also like to talk a few minutes about the margins of the Atlantic. So, what happens at the margins? Well, when the ocean drifts apart, when the ocean spreads, then the margins on either side are initially passive margins. Nothing much happens at them, apart from the fact that we might have some instabilities, some landslides. And here where it says in our top left panel where it says sediments, this is the passive margins. And all of Norway has a passive margin. And we'll talk a little bit more about this over the next few minutes. Passive margin means there's no volcanism, there's no major activities, but material is usually shed from there into the ocean basins. And this can be in form of very small drizzles of material, or it can be in form of large, large landslides. And there's evidence for a very large landslide that came off Norway several thousand years ago. And this is the Storegga slide, or slides, depending on whether you want to see this as one event or several events. And the red area in the map to the right, that's the Storegga slide. And it came off the coastline of Norway along the passive margin, and it created a tsunami that caused tsunami sediment deposits in the Shetlands, in Orkney, in the Faroes, and several tens of centimeters thick and several tens of meters above the shoreline. So this must have happened about 6,200 years ago, and it probably involved a 290 kilometer long section of coastal shelf, and it produced a volume of some 3,500 cubic kilometers of material that was slumping into the ocean. So if this would happen today, it would be quite a disaster, because it would affect most of the coastal areas in the region where we are sailing just now. So, but I should point out that mature oceans, they are not just spreading, mature oceans are subducting at the margins. And the Pacific is often also referred to as being surrounded by the ring of fire. You have subduction, old oceanic plates are sinking under their own weight after a certain amount of time, and then they're sinking back into the mantle, and this is called a subduction. The plates need to be pretty old for that, usually about 180 million years. Then they are mature enough to sink back into the mantle, and the Atlantic has almost no subductions at its margins, showing us that the Atlantic is still a very, very young ocean. There is one exception, and that is very intriguing. It's a wonderful natural laboratory, and that is the Antilles, the Lesser Antilles here, because their subduction in the Atlantic has just started. We have an island chain. This is the Lesser Antilles, some beautiful areas there, Guadeloupe, Martinique, Dominica, etc. And this is where we have the oceanic plate, the Atlantic plate, submerging under the Caribbean plate, and this gives rise to a different type of volcanoes. Now, one of the exam questions that we sometimes ask for our fourth-year students is, what will happen along the eastern and western seaboards along the Atlantic margins. And then our geology students have to think about what will happen in the future. And the answer is there will be subduction zone volcanoes all along the margins of the Atlantic in the next 20, 30 million years. So geologically, this is what we would predict. And indeed, this is what I think will actually happen with the margins of the Atlantic in millions of years to come. So here's a little diagram. It's very complicated. I don't need you to go into details at all. But here the Atlantic Ocean spreads with 2 centimeters a year. It's pushing against the Caribbean plate. And of course, scientists are really excited. This is why I'm showing this, trying to unravel all the processes going on and how these new subduction zones form. And that gives us a lot of information to predict about more mature systems like the Ring of Fire in the Pacific. So, I talked about plumes. Well, we looked at mid-ocean ridges now. We looked at subduction zone, and I'd like to bring you back to plumes, like the Iceland plume, just for a very quick minute. And the Atlantic is actually littered with plumes. And in the map to the top right, all these yellow-red dots, they are little plumes. And of course, Hawaii is the archetype of a plume system. But here in the Atlantic, we have a few as well. There's Jan Mayen, there's the Azores, there's the Canaries, there's Santa Helena, where Napoleon spent the rest of his life, and Tristan and several others. And here I have a little map from the Canary Islands where we see the ocean magnetic anomalies. They're marked with ages. And here we have a plume track cutting across. So there is a stationary heat anomaly, and the plates are moving ever so slightly. And this is like a Bunsen burner underneath a moving object. And it gives rise to these little island chains that we see also in the Atlantic. In the Pacific, the island chains are much more strung out because the plates are moving a lot faster. In the Atlantic, they're more clustered. And here's another example just from a little bit further south in the Atlantic, the Whalefish Ridge. And here's a little island called Tristan da Cunha, TDC abbreviated here. Sits close to the mid-Atlantic ridge, and it gave rise to a whole track of little islands and submerged little volcanoes that span all the way to Africa. And here we have these plume tracks in the Atlantic as well. So Iceland is not the only one, but Iceland is the most prolific one. So let me summarize the geology before we move to human travel on the Atlantic. And here, a good, really mature ocean has 3 types of volcanoes: rift volcanoes, plume volcanoes, and eventually also subduction zone volcanoes. And the Atlantic has rifts and plumes, and also just the very first subduction zone volcanoes in the Caribbean area. And this is signaling that the Atlantic is just about coming of age now when it comes to become a proper ocean.